Go relearn calculus. Okay. Let's make sure we cover the material we need to for today. But sounds like we're good to go. Topology sounds like that's the way we're leaning, and then we can bail out do a Western philosophy after you guys have had enough of a break. You need a break. And I assume when you say that you mean the school year.
Yeah.
Yeah.
Would you want to? I probably should have started this. Would you want to do it during the winter break?
Well, how fast could you do it?
Yeah.
Oh,
Like for quite a few weeks.
Oh, it's
Okay.
a month break, I remember.
yeah, it's an entire month. That's why I was thinking could get a good amount in that time. But yeah, people are gonna be gone. Never mind. So and I'm assuming you're gonna want to pick up again after the school year. Probably.
Yeah.
It's a lot of commitment.
Yes, if you start something out, do something during the summer.
Okay. So yeah, maybe we can just plan topology throughout the course and then plan again come summertime what people are feeling. Sounds like the heavy lean is Western philosophy, but maybe you want to do something like linear algebra, or who knows. Or even a physics. That's another
Okay,
that's
yeah, that is another one. Because I have not done physics. And that's...
Is physics one that suddenly captures a bunch of your interest and you're like, oh wait, if that's not an option on the table, I don't want to do that?
I would
Because
love
honestly,
Interesting.
It's so great to take a course like that. It's the one that gives you your foundations to all science. It's like the same way that you need to understand logic for all of math. And someone who doesn't understand logic and axioms, you know, they're really missing something when they're doing their math. Similarly, if you don't understand physics, you're really missing something when you're doing science. It's the foundation of all of it. So,
Yeah, physics would be fun too.
but you still want to break either way, right?
Yeah.
So, continue topology for now, and then we'll re-talk come the end of the school year, probably something like physics or a philosophy course. But for sure you don't want to do physics instead of topology. You'd rather do,
We've
I'd
built
rather do
it
physics.
up. So I feel like we might as well go ahead.
say that again?
We've kind of built it up, we're ready. Like,
For topology?
yeah, we just got through all of
Okay. Yeah, so yeah, when we finish this, we'll move to topology. And then who knows how long that'll take, so we'll see where it goes. Alright, so for sure, I'm gonna go get my chisel, put it in stone, topology. Okay, let me scroll my book up back to start.
I just have a jackhammer.
I don't need the book, we can just talk about it. Okay, so last time we were talking about sets, and we got comfortable with all the different operations on sets, intersection, union, subset, proper subset, etc. So now we're going to be talking about very particular type of sets for today and actually for next week as well. And these types of sets are called relations. The intuition for a relation is it's just a set of ordered pairs. Well, I guess we need to work out when ordered pairs first. We'll just follow this instead of me trying to do high-level view of the lecture. Let's just go through it and then we'll be done. Okay, so an ordered pair. So you notice when we were talking about sets, order didn't matter. The set 1, 2 is equal to the set 2, 1. Order didn't matter, duplicates didn't matter. So now we're going to come up with some sort of abstraction, some sort of mathematical model where we can keep track of an order. So if we want some sort of ordered collection. And so we're going to start out by coming up with an ordered collection that has at least 2 objects in it, and that's what we mean, but that has 2 objects in it, and that's what we mean by an ordered pair. So we're going to use parentheses. Another common notion instead of parentheses is angle brackets. You've probably seen both those. Ordered pairs, where have you seen ordered pairs before?
Graphs.
Graphs, points. Anytime we represent a point in the xy plane, we're using an ordered pair. That exact thing is what we're talking about when we're talking about an ordered pair. An ordered pair, what's our encoding for it in terms of sets? This is what it is. Now notice, if I give you this set, doesn't matter what order I put it in, you can always tell me which of those is supposed to come first, which of those is supposed to come second.
Right.
This one is the x element, this one's the y element. Or you can see what the y is from
Why
this.
does y have x in
Huh?
it? Why does the y element have x in it?
So you're saying why isn't this our encoding?
Yeah.
Because now I don't know which one comes first and which one comes second. if I do this, notice the smaller of my two sets is always the first one. And then if I want my second element, it's just everything that's in this set when I subtract away this set is one way that you can find it. Okay? So this is our encoding for it. From here on out, we'll just use this kind of notation. So now we know how to create an ordered pair, and we know the order of the things in there. So, and notice, x, y, this ordered pair is equal to this ordered pair if and only if x is equal to u and y is equal to v. That left-hand thing has to be equal to that left-hand thing, and that right-hand thing has to be equal to that right-hand thing. How would you prove that? Go back to their set definitions. So if I want this set to be equal to this set, then that set has to be equal to that set, and that set has to be equal to that set, making all their elements the same.
Right.
Right? It'd be a pretty basic proof if you want to do it. One more thing to note is order matters in these things. So let's look at the order pair 1, 2. The order pair 1, 2 is equal to the set containing the set containing 1 and containing the set containing 1, 2, which is not the same thing as a set containing the set containing 2 and the set containing 1, 2. These are fundamentally different. So 1, 2 is this set, which is different from this set, which is 2, 1. Right?
Right.
Fundamentally different order matters. And then obviously duplicates, well, we don't know how to do 3 yet, so never mind, let's get to 3. An ordered triple. So we know how to create an ordered pair of things. How do we create an ordered triple of things? Easy, an ordered pair within an ordered pair. So this is shorthand for this. And in general, if you're talking about an n-tuple, that's what we call this. Another name that we use a lot is a list. That's what we're going to, when we get to this in discrete math, we're going to call these things lists. An order collection, list, or n-tuple, n being the number of elements in there. How do we encode the n-tuple x1, x2, all the way to xn? Are you good with this is just signifying n elements in there? You use that kind of notation?
Yeah.
Okay. So we encode that where the left-hand thing is the n minus 1 tuple with xn out there. So it's a recursive definition. You understand what I mean by recursive definition?
Yeah.
You need to apply the definition over and over again. So this is equal to this thing, but what's that equal to? Plug it in again. So here's an example of it. What is this shorthand for? This is shorthand for this, but how do we rewrite that order triple like this?
Right. Right.
Right? So it's an ordered pair inside an ordered pair inside an ordered pair. That's what this recursive thing is saying. You keep doing that until it's just ordered pairs within ordered pairs within ordered pairs. In other words, everything is an ordered pair. Because that's the only thing that we have is ordered pairs. Okay? So that's how you define it. So from here on out, this is just shorthand for this. And you can treat this exactly how you're used to treating it. And so notice one more time, something like, oh, I have it right here. So when we were talking about sets, 1, 2 was the exact same thing as a set 1, 2, 2. But notice that 1, 2 is way different than 1, 2, 2.
Right, because
Right?
it's an ordered pair and an ordered pair.
And the intuition for that is the point 1, 2 on the xy plane is way different than the point 1, 2, 2 in the xyz plane. In 3 dimensions. Right? This is a point in 3 dimensions, this is just a point in 2 dimensions. So even your intuition for where you see these things coming up tells you no duplicates matters and order matters.
Yeah.
Okay, and then we can now define a finite sequence. S is a finite sequence if and only if there exists some natural number such that there exists some natural number n such that S is an n tuple. In other words, every one of these things we can call a finite sequence.
Right.
Right?
No.
What can we call them?
The your first one that you pointed out.
This right here is a finite sequence.
No, use it.
That's exactly what we're saying here.
Okay.
Any n tuple where n is some natural number is a finite sequence. And it's a sequence with n elements in it.
Seems like, yes, makes sense actually.
Good? We'll go with a different definition in calculus when we get there. A way I like more. So, now moving on to another operation. Now we have order pairs. Another operation that we use all the time on sets is the cross product. So if A is a set and B is a set, the cross product of A and B is a set of all ordered pairs where where the left-hand element comes from the left-hand set and the right-hand element comes from the right-hand set. So let's see an example, then we'll go back to the definition. Let's say that A is a set 1, 2, 3, and B is a set square triangle. Then A cross B is a set of all the ordered pairs I could possibly get using A for my left-hand elements, 1, 2, and 3, and B for my right-hand elements, square triangle, square triangle, square triangle.
Right.
Notice that this is every possible thing I could get, all the ordered pairs I could possibly get, where my left-hand element, the ordered pair, comes from A, and my right-hand element comes from B. Does any part of that not make sense? Is this going? Yeah. Okay. So, that's what we mean by the cross product of two sets. And this is something that comes up again and again. Those of you taking discrete math, we're going to do a lot with that when we get to it, so it's a concept that doesn't go away in math. Okay. So now we have a concept of a relation. So an n-ary relation, where n's some number, some natural number between 1 and whatever, relation is a set of n tuples.
I thought that was a finite sequence.
So for example, this right here, notice that everything in this setup here, A cross B, everything in there is a 2 tuple,
Yeah.
or an ordered pair, a 2 tuple, same thing. 2 dash tuple is an ordered collection with 2 things in there. Am I losing you in just terminology?
Yes. I'm confused what you're saying.
So everything in this set right here is a 2 tuple. That's a 2 tuple, that's a 2 tuple, that's a 2 tuple. All the things inside this set are
Because
2
it just has
tuples.
2 pairs.
Because it's an ordered collection with 2 elements.
Okay.
That's what a 2 tuple is. We have a special name for 2 tuple, ordered pair, but in general, if an ordered collection has n elements, we call it an n tuple.
Okay.
We just have a special name for one that only has 3 and one that only has 2. An ordered pair, an ordered triple, then we would call it, if it had 4 elements, we call it a 4 tuple. If it had 20 elements, we call it a 20 tuple. So this right here is a set full of 2 tuples or ordered pairs. Same thing, right?
Right.
So this is a 2-nary relation, or we have a special word for 2, bi. So it's also a binary relation. This one is. If each of these had 3 elements instead of 2 in them, then this would be a ternary relation or a 3-ary relation. You understand what this is trying to say?
Mm-hmm.
Yeah.
So, is this a relation?
Yeah.
Yeah.
What kind of relation is it?
Ternary.
A ternary relation. That works. Or a 3-nary relation.
That's a
Whatever
bi.
you want to call
No, it's not.
it. What?
Bi's 2, bro.
Bi's 2.
Yeah, but I thought we were just looking at the ordered pair. Oh, sorry.
That's an
set.
ordered triple. Ordered triple.
Yes, sorry, those are.
Now what if I got rid of that and got rid of that? Okay, now what is it?
6.
6.
That's a 6 tuple inside of it. What about this whole thing though? Is this a 6-nary relation?
Uh-huh.
No.
No,
Because it
it's
doesn't
a
have-
set of n
doesn't have-
tuples.
Yes, it is.
Yes, it is.
It is?
It's a set containing one 6 tuple.
Oh, okay.
Everything in the set is a 6 tuple.
The fact that you say n tuples and like it has an s at the end doesn't mean it has to be more than one.
Well, and put one in for.
No, that's me being lazy. It's a set where everything in the set is an n tuple.
Okay.
That's how I should put that language. So, is this a 6-nary relation?
Non-nary relation.
Yeah, it's a 6-nary relation. It's a 100-nary relation. Everything in there is, finish the sentence however you want. And it's true.
What?
Everything in this set is a purple dragon. If it's in this set, then it's a purple dragon. If it's in this set, then it's an n tuple. If X is in the empty set, then fill in the blank. If false implies whatever you want here, it's always going to be true. Right?
Yes.
Yeah.
So it counts as an empty n-ary relation for any relation you want to talk about. Good? That's probably like the one doxy case. Now, we don't care about these n-ary relations from here on out. The only one we care about is called a binary relation. And from here on out, anytime I say the word relation, I just mean a binary relation. So a binary relation is a set of ordered pairs. That's all it is. It's a set where everything inside there is an ordered pair. This counts as a relation. It's everything in there is an ordered pair.
Yeah.
Right? Okay. So from here on out, I'm just going to call them relations. I'm not going to say binary relation anymore. If I say relation, we're talking about a set of ordered pairs from here on out. Those are the only ones we care about. Good?
Yep.
So let's look at some examples of relations. Let's say R is equal to the set 1, 2, 2, 3, 1, 0. Is this a relation?
Yes.
Yeah.
Okay. Now let's do it the other way. Let's deal with the relation that you've been using your whole life, and let's write out what that might look like. You've used the less than or equals relation 1,000,000,001 times, right?
Yeah.
You've been counting. You're up to 1,000,000,001. So what are some of the things inside this?
1, 2.
1, 2. Yep, that's in there. What's something else in there?
2, 3,
2, 3's in there.
0, 1.
Okay, let's stop being so predictable. Negative 97. That's in there, right? Because that is less than or equal to that. Another thing in there, 1, 1.
Right.
And there's infinite things in there. That's the relation we mean by the symbol. We mean this set. It's an infinite set. We don't want to write out the set. So we have a shorthand way of writing out that infinite set. Here it is. It's a relation. It's a
Wait.
set of ordered pairs. That's what the symbol means, less than or equal. Shorthand for set of ordered pairs. Good? Now this is not exactly, well, I think I can say exactly like. This is exactly the things that we were talking about with predicates before when we were doing logic. Give me an example of a predicate that we were talking about all the time that had two things.
Greater than.
Greater than, or taller than. We might say that Jacob is taller than, using T for the taller than relation, Donnie. What do we mean by that? We mean that TD is an ordered pair inside the taller than relation. Oops,
Is it
JD. Jacob and Donnie is an ordered pair inside this taller than relation if it's true that Jacob is taller than Donnie. This is shorthand for expressing this statement. That's what we mean. Right? What's another one? Loves. Jack loves Jill. Jack loves Jill. What do we mean by that? We mean the ordered pair Jack, Jill is in the loves relation. So anytime we were talking about relations, you could have been thinking about these sets of ordered pairs behind the scenes. And for those of you that took discrete math, you were probably already thinking about it that way. But, so all our predicates now, we can just think about in terms of relations. And the ones we're most interested in are binary relations, so all our binary predicates we can think about as binary relations. And to say that x is related to y means that the pair xy was in that relation. Feel like we got some intuition for what relations are? Alright, so let's continue with some of the properties relations have. So, let R be a relation and let A and B be sets. Good so far? We say that R is a relation on A, provided that R is a subset of A cross A.
R is a relation.
Yeah, let's really quick draw something over here to help this make sense. So let's make A, what set should we have it?
1, 2.
1, 2. Alright, there's A. Let's make R equal to, in this case, then 1, 1, and 2, 2.
It's a relation, it's not a set.
Relations are sets.
A relation is a set of ordered pairs.
Oh, right.
Everything we're talking about, it's always a set. An ordered pair is a special type of set.
Right.
A relation is a special type of set. It's always sets. So, here's A, here's R. Now, what's A cross A?
1, 1.
1, 1's in there.
1, 2,
1, 2.
2,
2,
1,
1,
2, 2.
2, 2.
Perfect.
Ah.
It was a set of all the ordered pairs that you could possibly make where your first element comes from A and your second element comes from A. Alright? So A only has 1, 2. So what are all the ordered pairs we can make where the first element is 1 or 2 and the second element is 1 or 2? These 4. And that's it.
Then what was R?
R is this. So I pick R and I pick A.
It's a subset.
Here's A cross A. Is it true that R is a subset of A cross A?
Yes.
Yeah.
Yeah.
Okay, so since it happens to be the case that R is a subset of A cross A, we say that R is a relation on A. In other words, R, if you look at R now, it's only relating things in A to other things in A. Right?
Yeah.
Yeah.
So, for example, if we were to do the sitting next to relation in this class, we would make A equal to all the people in here, right? We'd have Jacob, James, Peter, Ammon, Leah, and Emma. There we are. And then our relation would be, let's see, we've got Jacob is sitting next to James. We've got James is sitting next to Jacob. Notice that you have both those.
Mm-hmm.
And we can continue on our way, iterating everything in there. Notice that this is going to be a subset of A cross A.
Mm-hmm.
All our left-hand elements are going to be people in this room, and all our right-hand elements are going to be people in this room. So this is an example of creating a relation on a set A. You with me?
Yeah.
What?
He's trying to read that. Like, put it into words.
Oh,
Besides spell.
Jajumpel?
Yeah.
Yeah, for sure. Okay, so let's go back to this. I think you understand the first part. Let R be a relation and let A and B be sets. We say that R is a relation on A provided that R is a subset of A cross A. And we say that R is a relation from A to B provided that R is a subset of A cross B. So let's do an example with that. How might we do an A cross B? Let's have A be the people in this class. We can make B equal to the set of natural numbers. And then we can make our relation is the age of. And so James is the age of some natural number. So we make our relation would be something like,
Oh.
James, how old are you?
19.
19. Oh, oops, that's Jacob. Well, Jacob, you're 19 too. And James is 19. And Peter, how old are you?
I'm 16.
16. And we continue
17
on our
and
merry
2
way.
is 2.
So you see what this relation is?
Yeah.
Now notice, A cross B, what is that? That's massive. We need to take James, or Jacob, and we need to pair him with every single natural number. And then
Right.
James and pair him with every natural number.
Right.
And Peter and pair him with every natural number. If we do A cross B, that set, it's going to be an infinite set, right?
Mm-hmm.
But the relation.
Do you see how that's going to be an
So
infinite
what you're
set?
saying is I can be 19.
Well,
If we do
can
A
pair
cross
it
B,
with natural
we're going to get Peter paired with the number 19. This relation captured is the age of.
Right.
This is the only one saying is the age of. Down here, we're just putting people and numbers.
I see.
So a relation is trying to capture some particularly useful way of relating two elements from a set. So we might pair you with 16 when we're talking about your age. We might pair you with 120 if we were talking about your weight, or however much you weigh. So we can make another relation that uses weight.
Yeah.
Really raise your eyebrow on that one. Is I way too high or way too low? Or anyways, doesn't matter. So this relation would be a subset of A cross B. All its left-hand elements are going to be people in the room, or they come from A, and all its right-hand elements are going to be natural numbers, or elements of B.
Makes perfect sense.
So do you all feel like you understand what a relation from, or a relation on A is, and what a relation from A to B is? And it's all based on understanding the cross product. So the cross product, it comes and stays, never goes away. Okay, so let's look at some examples with just numbers. I think it helps the intuition more to include things that aren't numbers, but now let's just look at numbers. And let's go out there and say whether it's, so here's a bunch of relations. You're going to tell me what it is. So let's look at this one. What's this relation?
A to A.
It's on A, right?
Yeah.
So this is a relation on A. Everyone understand?
Yeah.
Every left-hand element in this relation is an element in A. Every right-hand element in this relation is an element of A. Therefore, it maps elements of A to elements of A. It's just pairing elements of A with elements of A. So it's a relation on A. That's what we mean. It's a subset of A cross A. All its left-hand elements came from A. All its right-hand elements come from A.
Yeah.
Okay? Next one.
Trick question.
On A.
It's also on B.
Well, 4 is, but it's A is on the left hand, but
It's
B is not.
on A.
Yep, it can't be on B.
Because 1 isn't on B.
Yeah, one is on
Let me write one more relation here to the side. What's that relation?
It's on both. It's on A
On
and B.
A and on B.
Yeah, you can call this a relation on A, you can call this a relation on B, you can call this a relation from A to B, you can call this a relation from B to A. You can call any of those things. Because it works for all those, right? It's a subset of A cross A, it's a subset of B cross B, it's a subset of A cross B, it's a subset of B cross A.
Yeah.
So there's no reason that it has to be just one of them. Make sense? Alright, next one. What's this?
from A to B.
Yeah, this is going A to B. What's this?
From B to A.
B to A.
B to A. And what's this?
Both A to B
A
and
to B and B to A.
Isn't it?
None.
Yeah.
It doesn't have to be one of those.
A doesn't
It's
have-
just if the relation happens to satisfy this condition, then we say it's a relation on A.
Right.
If it happens to satisfy this condition, then we say it's a relation from A to B. So don't start thinking it's got to be one or any or both. It's just if it happens to meet the condition, then it's that too. All right. So we feel like we're pretty comfortable with a relation being a relation on a set versus it being a relation from a set to a set.
Pretty good, pretty good, pretty good.
Okay. So some terminology now that you're probably already pretty familiar with. The domain of a relation. We call the domain of a relation the set of all its left-hand elements. Okay? So let's erase our stuff up here real quick and then write out the domains of each of these. So what's the domain of this?
1, 2, 3, 4.
Yeah, it's just 1, 2, 3, 4, or A.
Mm-hmm.
What's the domain of this?
1, 4.
1, 4. What's the domain of this?
1.
What's the domain of this?
B.
4, 5, 7, 6. And what's the domain of this?
1, 7.
1, 7. Alright, so there's the domain of those relations. So you understand what the domain is. Now let's wrap our head around the definitions, make sure you understand. Let R be a relation, then the domain of R is a set of all x where there exists a y such that x comma y is in the relation. It's all the left-hand elements where there is a right-hand element that's paired with it in the relation. Right?
Yeah.
So 15 is not in the domain of this thing because there's no y paired with, there's no right-hand element paired with the 15. There does not exist some y such that 15 comma y is in this relation.
Right.
Feel like you understand this definition?
Yeah.
And we have a shorthand for referencing the domain of relation. We just do dome, parentheses, the relation we're talking about. That's shorthand for this set or this set, depending on the relation we're talking about. Does that make sense?
Mhm.
Does it, James?
No.
What part of that doesn't make sense?
I wasn't listening.
Do you know what the domain of a set is, or of a relation is?
Yeah.
Yeah, it's all the X.
All the left-hand elements.
Yeah.
It's every x such that there exists a y where that y is paired to that x. So you understand now?
Yeah.
Easy peasy. Alright. The codomain is probably exactly what you guessed it is. It's all the right-hand elements. So it's all the y where there's an x paired with it in the relation. Huh?
So it's the range.
Yeah, isn't it called the range?
That's for a function.
We're talking about ordered pairs.
A function, we're going to get to functions next week. A function is a special type of ordered pair. So an ordered pair is a special type of set. A function is a special type of ordered pair.
Oh, because aren't functions you put in something and you get something out?
Well, that's how they say it to elementary students, but
Yeah.
Dr. Seuss.
it's for every x, there's a unique y paired with it
Yeah.
inside a relation. So if I have a relation where that's the case, then yeah, it's a function.
The one I'm
But we'll get to that.
comfortable with is range.
Range is typically associated with, we'll get to the difference between codomain and range. And we're going to have to talk about a function from a set to a set instead of just a relation from a set to a set. So we'll get there. And then the field, this is one that you never even heard of in discrete math, but the field is just the union of the domain with the codomain. Does that make sense?
What does union mean again?
It's in this set or it's in this set.
Oh.
So if we're looking at this one, the field is just the numbers 1, 2, 3, 4. If we're looking at this one, the field is 1, 2, 4. If we're looking at this one, the field is 1, 4, 5, 7,
Yeah.
etc. It's everything that was in the domain or in the codomain. Because in one of those two, it's in the union. Does that make sense?
Sure.
Okay, so I was going to do examples down here, but we kind of hit the point home up there, I think.
Yeah.
We need more examples, but I think we're good. So we'll move on. An inverse relation now. So let R be a relation, then the inverse relation, which we denote R to the power of -1. You've seen this with functions before. Same exact thing, a function is just a relation. So let R be a relation, then the inverse relation, R to the power of -1, is the set of all the ordered pairs x, y, where y, x was in R. In other words, flip them all around. So let's write the inverses of the relations up here real quick.
One more.
So what's the inverse of this relation?
Same one to this.
It is exactly what it is. You notice if you take all these and you flip them, you still just have 1, 1, 2, 2, 3, 3, 4, 4. Let's look out for this one.
2, 1.
2,
2,
1,
1,
and
2,
2,
4.
4.
Yeah, maybe there's no point in me even writing it, huh?
Yeah.
So good at this. Pro mathematicians right here.
Yeah, you guys just run off to graduate school, get your PhDs, you ready to go?
Let's do it.
All right. What would it be for this?
4, 1, 5, 1, 7, 1.
Yeah.
All right, so I think you get the point. Just flip the elements around. That's what we mean by an inverse relation. So, question. What does the inverse of the inverse equal?
The
Same thing.
R.
R.
Just the relation itself.
Mhm.
If you flip them all around and you flip them around again, you're back where you started.
No.
We'll prove that in discrete math. Okay, so we don't need examples of that, we can just use those. Some notation that I've already been using, I think,
X are.
Oh, we've already seen it because we've been using it with predicates. So, notation, if I want to say that x, y is in the relation, I just do x is related to y.
Right.
And you're used to seeing this with predicates, and you're used to seeing it with relations, such as less than or equals. If I want to say that x and y are in the less than or equals relation, the way we typically say that is x is less than or equal to y. So it's very common when we're talking about relations, we put the relation between the two things that we're saying are in the set. So this is shorthand for this. Okay. Now some properties that relations might have. Relations on a set. So now we're going to limit ourselves to talking about a relation from A to A. So when we're talking about these properties, we're only talking about relations like this. From A to A. Good?
Oh, I forgot all that.
Well, now you'll remember. Okay, so a relation R on A, we call it reflexive if X is related to X for every element in A.
Okay.
So here's what we're going to do. We're going to go over the property, then we're going to go over each of these relations and say whether or not it has a property.
Okay.
Okay? So, reflexive means for every X in A, X is related to itself.
Right.
So, is every X less than X?
No.
No.
No. Is every X a mother of X?
No.
No.
No. Is every X divisible by X?
Yes.
Yes, X divides X. 9 divides 9. How many times does 9 go into 9? Once. Is X the ancestor of X?
No.
Is X less than or equal to X?
Yes.
Is X equal to X?
Yes.
Is X in there?
Yes.
Well, I asked that one weird. How can we say it for this one?
If X is in A,
Is, if I know that A is an element of A, is A inside of A cross A?
For sure.
Yeah.
For sure.
Yes. Right? Let's come and look over here real quick for, let's see, this was the only one on A, right?
No, the second one was on A.
This was on A and this was on A.
Yeah.
So we can also, so we'll do it for these relations and then for these two, where A is that right there. Is this one reflexive?
Yes.
Yes, for everything in A, so 1's in A, is 1 related to itself in this relation? Yep. Is 2 related to itself? Yep. Is 3? Yep. Is 4? Yep. What if I get rid of this? Is it still reflexive?
Yes.
No! If for every element in A, that element is related to itself, then it's reflexive.
What? I thought. Okay.
4 is an element in A, 4 is not related to 4 down
I
here.
thought related means it's just a subset. And
Remember now we're talking about R is a relation on A. Then for every element in A,
Oh yes.
X is related to X.
There you go. Yeah.
So for every element in A, for every element X in A, for every element X in A, X comma X is in R. Then R is reflexive on A. So this is not reflexive. We have to have 4 comma 4 there for it to be reflexive.
Yes, sir.
Make sense? It has to take every element in A and map it to itself in order for it to be reflexive. Parallel to itself. Sorry, probably shouldn't say map. So we feel like we got reflexive? All right, let's move on to irreflexive. The relation R is irreflexive if for every X, X is not related to X. Now notice that these two are not opposites of each other.
Right.
Reflexive means every X is related to itself. This means every X is not related to itself. If some X's are related to themselves and some aren't, then it's neither.
Right.
Make sense?
Yeah.
So
Well,
it
like.
has to be.
It does not have to be one or the other. These are not opposites.
Right. Because line 2 is irreflexive.
Oh yeah, we didn't finish on reflexive. We said this one's reflexive. What about this? Is this reflexive?
No.
No. Because it would have to have 1, 1, 2, 2, 3, 3, and 4, 4 in there to be reflexive.
But
But
it is
it is
irreflexive.
irreflexive.
Yeah, so this one is irreflexive. Let me add one
Wait.
element to it real quick so that it's more interesting. Let's put 3, 3 in here.
That's what they all say.
3, 3. So now that one has 3, 3 in it.
That is not irreflexive.
It's none. It's neither.
Yeah.
So now, not reflexive, not irreflexive. This one is reflexive, but not irreflexive. Let's go over these ones to say which ones are irreflexive.
But to be irreflexive doesn't have to, it has to be every element in X.
Every element in A cannot be related to itself. So we kind of assumed that you knew what the A's were when I was talking here. When I'm talking about less than, what's my A? All real numbers. When I'm talking about is the mother of all people who have ever lived. When I'm talking about divides, all real numbers. Is ancestor of, I'm talking about all people. Less than or equal, I'm talking about all numbers, all numbers. Here I'm talking about whatever A is. Good? So let's go over it real quick. Is less than irreflexive?
Yeah.
Yes, it is never the case that a number is less than itself. That's never the case.
Okay.
X is never less than X.
Right.
So since it's never the case that X is related to X, for all X, X related to X is false. X not less than X is true. I don't know. I'm trying to come up with a bunch of different ways of saying the same thing.
Yeah.
Does it make sense that this is irreflexive, or are we missing something still?
No, that makes
Makes
sense.
sense.
All right. Is the mother of? Is this irreflexive? Is it possible for someone to be the
No.
mother of themselves?
No.
No, they can't be the mother of themselves. That's
No.
impossible. So it's irreflexive.
It's
No.
your society, maybe. That is irreflexive.
Is it?
Yes. Because it's impossible for the relation to occur.
I really got you guys confused.
Yes.
It is irreflexive,
That's what I said.
right?
Yeah.
Yeah.
Okay.
Paused.
So let me say it this way. While it doesn't have to be reflexive or irreflexive, it's impossible to be both, right?
Right.
But still.
So, is X the mother of X? Is that ever the case?
No.
No.
So X is never related to itself.
Yes.
Yeah.
So X is never reflexive. So it's
Yes.
irreflexive.
Yeah.
Maybe that's a way to help say it.
That's beautiful.
Okay.
You getting it?
She
A
was
little
like,
bit. It's coming.
Carol, comma, Carol never satisfies this relation.
Yeah.
If I take the same mother twice and put it on, or the same female twice and put her on either side of this is always false. No female is a mother of herself.
Yeah.
So it's irreflexive.
Yeah.
So it was this, it was not this. But it doesn't necessarily have to be one or the other. Okay, so this was irreflexive. This was irreflexive. What about this one? Is it irreflexive?
no.
No.
Because
Right.
for every number you can divide it by.
Because
Itself.
you just need one counterexample. If you can find one case where this happens, right? What's the negation of for all x not something?
In the
There
same-
exists x such that something.
Right.
So if I can find one x such that x is related to x, then this statement's false. Does that make sense what I'm saying?
Yeah.
Right, how do I disprove all swans are white? Find one swan that's not white, and we're done.
Right.
How do I disprove that this is irreflexive? Find one case where a number divides itself. In other words, 2 divides 2. We're done. It can't be irreflexive.
Why did you write that sign? Is that a division sign to you?
Not division, divides. Division is an operation, divides is a statement.
Yeah.
We're talking about the statement divides. 2 divides 6 is true or
That's
false.
how you write divide?
2 divided by 6 is 1/3.
Right.
That's a number. We're talking about divides, not divided by.
Yeah. And in divide you only use natural numbers or
Integers.
integers.
I don't know if there's some notion that carries over for rationals, but the case where I always have used it, it's been integers. Okay, continuing. is the ancestor of.
A reflective.
Irreflexive, yes. Less than or equals.
No.
No. 1 is less than or equal to 1. If you can find one case where it doesn't work, you're good. Equals.
No.
No. A cross A. No. Good? Alright. Symmetric. What does it mean for a relation to be symmetric? It means that if x is related to y, then y is related to x.
In every case? Or just one?
In every case. This being true implies this is true. So if you have this, then you have to have this.
Right.
Otherwise the implication is false. For all x, y in A. Sorry. I just got sick of writing that. Okay. Let's give you an intuitive example of symmetric real quick. Is a sibling of. If I am your sibling, you are my sibling. Sibling is reflexive. Right? So let's look at, is less than reflexive?
No.
No.
No. Is the mother of reflexive?
No.
No. Is divisible reflexive?
No.
No.
6 is divisible by 3.
2 divides 6. 6 does not divide 2.
Okay.
Is the ancestor of?
No.
No. Is less than or equal?
Yes.
Yeah, if 2 is less than or equal to 2, then 2 is less than or equal to 2, right? So it's symmetric?
Yeah.
But then
No, it has to always be the case. It has to be the case that every time x is related to y, then y is related to x. So I have 1's less than or equal to 3, but 3 is not less than or equal to 1.
But I thought it's A cross A.
it has to be a relation on A.
Oh, relation on
Yeah, in this case, a is the set of all numbers.
A. And X and Y are different numbers.
They could be the same, they could be different, they're just any two numbers.
Yeah.
So is it true for any two numbers that the first is less than or equal to the second, that the second is less than or equal to the first? No. What about equals? Yes, symmetric.
Yes.
If 1's equal to 2, then 2's equal to 1.
Yes.
It just so happens that 1 isn't equal to 2. But any time I find two x's and y such that x equals y, then it's also the case that y equals x. Good? And then A cross A.
Yes.
Yes, right? Looking at this, well, we don't have an A cross A right now, do we?
Yeah, we did.
Here's an A cross A, where A happened to be 1, 2. If 1, 2's in there, then 2, 1's in there,
Right.
right? Okay, so that one's symmetric. Moving on to asymmetric. Asymmetric, for those of you who've done discrete math, these were the ones that you didn't see before. You haven't seen this one, you haven't seen this one, and you haven't seen this one. So this is a new one for you. Asymmetric means if x is related to y, then it is not the case that y is related to x. Again,
It's not ever the case.
these are not, well, we'll go through them.
Less
It
than-
does not have to be one or the other of these. It can be neither. Okay? But it can't be both. Oops, lost my arrow there. So, asymmetric. If we know that x is related to y, then we also know that y is not related to x. It
Right.
means it's asymmetric. So let's go through it. Less than.
Yes.
Yes.
Yes, that one's asymmetric. If x is less than y, then it is not the case that y is less than x.
Yes.
Is the mother of?
Yes.
Yes.
Yes. Divides.
No.
Yeah, no, because you can have one counterexample. One
Yeah.
divides one, also one.
2 divides 2 and 2 divides 2.
Oh, right.
Or if you want two different numbers, 2 divides negative 2 and negative 2 divides 2. So divides is an example of one that's not symmetric and it's not asymmetric. Is the ancestor of?
Yes.
Yeah.
Yes.
Yes. Less than or equal?
Yes.
No.
No.
Oh,
3 and
that's
3.
equal.
If 3 is less than or equal to 3, then 3 is less than or equal to 3.
All right.
Equals?
No.
No.
No. A cross A?
Yes.
No.
Right.
If 1, 2's in there, is it the case that 2, 1's not in there?
Right. No.
No. It doesn't have to be one of these, but it can't be both. Right?
Anti-Semitic. What the heck?
Okay, don't rely on the names for intuition about what it's saying. The same way that irreflexive does not mean not reflexive. Those are not the same thing. Yeah, we have symmetric, asymmetric, and anti-symmetric. You would think it's either symmetric or asymmetric, right? No. And anti, why do they pick these words? Who knows?
Just against.
So, anti-symmetric means that if x is related to y and y is related to x, then they're equal. We'll go over some examples. All right, less than is less than anti-symmetric.
No.
No.
Oh, if one is, there's no such thing as two numbers that can.
Right, so your antecedent's always false. So yes, it is anti-symmetric. Anytime I have 1 less than 2 and 2 less than 1, I have 1 equals 2.
Fine. You also have purple dragons, so.
Now, if I have a purple dragon, then I have whatever I want. Oh yeah, you could also say it that way too, I guess. Okay, so this is anti-symmetric. Every time I have two numbers x and y, such that x is less than y and y is less than x, then I have that they're equal.
Okay.
Right?
If false and true.
Exactly. Is the mother of. Yes. If I have a woman who's her own mother, no, I said that wrong. If x is the mother of y and y is the mother of x, then they're the same person. Then they're the same person.
That's a little flippy.
Because no one is ever the mother of themselves, right?
Yes.
Divides.
Yes, actually.
No.
No, if one divides.
2 divides negative 2, and negative 2 divides 2. They're not equal. Anti-symmetric says that anytime you have x related to y and y related to x, then they're equal. We have 2 related to negative 2 and negative 2 related to 2, but they're not equal. Good?
Yeah.
Where were we?
Is an ancestor of.
Is an ancestor of.
No, or yes.
Oh,
Because it's not false.
Right, no one's their own ancestor. Unless there's some weird time travel going on. So this one is anti-symmetric.
God. It's their own ancestor. Technically. She married her grandpa.
No, it has to be a genetic line.
Bye.
She's a grandma of herself.
Even then.
Anyways, less than or equals.
That doesn't make sense.
Less than or equals.
If x is related to y.
If x is less than or equal to y, and y is less than or equal to x,
Yes.
then x is equal to y.
Yes.
So there's one that's anti-symmetric in the sense that you want them to be anti-symmetric. And I should have specified, talking about divides. Going back to divides, it's not anti-symmetric if we're talking about the integers. It is anti-symmetric if we're talking about the natural numbers.
Right.
So if we pick A to be the natural numbers for this relation, then it is now anti-symmetric.
Right.
Make sense? So what the A is definitely matters for these, and I probably should have specified to the side. But anyways, equals.
No. 1 equals 2 and 2 equals 1.
If 1 equals 2 and 2 equals 1, does 1 equal 2?
Okay, shut up.
That one's the most obvious of them.
Yeah, but
If x is equal to y and y is equal to x, x is equal to y.
okay.
Yes. Okay, A cross A.
No.
No, because we're going to have 1, 2 in there. We're going to have 2, 1 in there, but 1's not equal to 2. Okay, what were we on? Transitive. Now, we already came across the transitive property when we were talking about groups.
Right.
Groups? No, it wasn't groups. It's when we were talking about a weak preference. We were saying weak preference is transitive. So if x is related to y and y is related to z, then x is related to z. Good intuition for a transitive relation would be taller than. If Jacob's taller than Donnie and Ammon's taller than Jacob, Ammon's taller than Donnie. That's what we're saying. So we feel like we understand what transitive is saying?
Yeah.
Okay, so let's go through it. Is less than transitive.
Yes.
Yes.
Yeah. If x is less than y and y is less than z, then x is less than z. If 1's less than 2 and 2's less than 5, 1's less than 5. Is the mother of?
No.
No.
No. If Jane's the mother of Jill and Jill's the mother of Stephanie, Jane is not the mother of Stephanie.
She's the grandmother.
She's the grandmother. Divides.
2 divides 6.
Yes.
And 6.
Those of you in discrete math, you better know the answer.
Yes.
Yes, we proved it. Divides is transitive. If A divides B and B divides C, A divides C.
Right.
Is the ancestor of?
Yes.
Yes. If I'm your ancestor and Jane's my ancestor, Jane's your ancestor.
Finally worked. Nice.
Less than or equal?
Yes.
Yes. If 1's less than or equal to 2, 2's less than or equal to 3, then 1's less than or equal to 3. If x is less than or equal to y and y is less than or equal to z, x is less than or equal to z. Good? Equals.
No.
Yes.
If x equals y and y equals z, does x equal z?
No.
Yes. And then A cross
3, 1's not equal to 3.
A cross A.
Yes.
Is that transitive?
Yeah.
One's related. Let's pretend that we had A now is equal to. Let's just write 1, but we won't write all the elements in there. A equal to 1, 2, 3, 4, 5. We'll think about this for a second. So now, what's A cross A? It's all the possible order pairs that we can make using this for my left-hand element, one of these for my left-hand element, and one of these for my right-hand element, right? So, is A cross A going to be transitive?
Yes.
Yeah.
Is it true that if I have, give me one thing in there,
1, 2.
so 1, 2 is going to be in there, and then 2 something in there,
3.
3. So if I know that 1, 2 is in there, I know that 2, 3 is in there. Am I guaranteed that 1, 3 is in there?
Yes.
Yeah. Okay, so A cross A is transitive. Connected. This one's kind of a weird one. Before we do that, let's look over at this relation. Tell me if this one's transitive.
Yeah. No.
We got a no. Do we have any yes?
I don't know which one you pointed to.
Oh, sorry. This one.
At the very top.
Is that transitive on A?
No.
Does anyone think yes?
I want to.
I said no.
You said no?
Yeah. Peter says yes.
Peter says yes.
I heard him too.
Did you say yes? Come clean.
No.
No, you didn't? That's too bad, because the answer is yes, it is transitive.
Should.
Every time I have x related to y and y related to z, I have x related to z.
Oh, transitive, not
No,
connected.
not connected.
Oh, we didn't go with connected.
No.
We were singing
What are you
transitive.
guys talking about?
We were talking about transitive.
No, because 1 is not related to 3, Ruth.
But if you have to find a case where the antecedent's true. Every time the antecedent is true, the conclusion's true.
So there's no such thing.
Every time one.
Sure there is.
one.
You have 1, 1, and 1, 1, therefore 1, 1.
Yeah.
That's in there.
Yeah, you're right.
But don't they have to be different numbers?
No. There are just 3 things in there. They can be the same, they can be different. There are just 3 arbitrary elements. It's just like if you're solving the equation y equals x, you know that's just a line. You might say, well, but don't those have to be different numbers? That doesn't work. No, they could be the same. It's just variables.
That's what Jake keeps getting stuck
You're
on.
supposed to soon.
All right. Let's see. Now we're on connected. Okay. So intuition for connected is that any two things in there that aren't equal are somehow related to each other. Okay?
That are not equal are
Okay.
related to each other.
Yeah. Then either X is related to Y or Y is related to X, if they're not the same thing. That's
Oh.
what we mean by connected.
Perfect.
So let's look at less than. Is less than connected?
No.
Yes.
Yeah.
Yes.
No.
You're outvoted.
It's not equal.
Is it true that anytime we have two numbers that aren't equal, we either have X is less than Y or Y is less than X?
Either or and/or.
That's an or.
Okay, yeah, you're right.
Okay, is the mother of.
Yes.
Yeah.
Is it true that for any two people, if they're not the same person, one of them is the mother of the other person?
No.
Are you Anna's mother? That's two random girls who aren't the same person. So it would have to be for any two females that you picked, that relationship holds as long as they're the same, for it to be connected.
Doesn't have to be females.
Well, if we're doing is a mother of, it has to be females.
We gotta get woke here.
Well,
Divides.
No.
They're not equal.
No.
Yes.
No.
Yes.
What about 3 and
no.
4?
No.
Yes.
3 and 4. Wonderful. Pick two numbers. 3 and 4. Is it true that 3 divides 4 or 4 divides 3?
No.
No. For those of you who have heard the term relatively prime, just pick two relatively prime numbers. Right, James? Why do you even want to continue the class?
I love listening.
Alright.
You know,
Is the ancestor of. Is it true that if you have two people who aren't the same person, one is the ancestor of the other?
No.
No.
Alright, less than or equals?
If they're not equal, yes.
Yes, right? Alright, equal. I think Jacob can figure this one out.
No.
Alright, no, that one's not connected. And then A cross A, is that one connected?
Yes.
Yes. Pick any two elements in A
That are equal.
that aren't the same. So pick any two elements in here that aren't the same. 3 and 4. Is 3 comma 4 going to be in here? Yes. And then strongly connected. So the only difference between connected and strongly connected is strongly connected, we don't care if they're equal now. They can be equal or they're not equal, we don't care. You go with the difference between those? So let's go through them. Less than. Is it strongly connected?
Yes.
No! Because now they can be equal. Pick 3. 3 and 3. Is it true that 3 is less than 3 or 3 is less than 3?
That's so rare. We're never gonna find that one.
We'll see. Is the mother of. Is that one strongly connected?
No.
No.
No. Divides. Is that one strongly connected?
No.
No.
3 and 4 again.
Is the ancestor of. Is that one strongly connected?
No.
Less than or equals. Is that one strongly connected?
Yes.
Yes!
So the only one.
So anyone that's connected, anyone that's strongly connected is also connected.
Yes. Okay.
But not vice versa.
Right.
And then, oh, maybe what I said isn't true.
Because equals isn't connected.
Oh, we lied. Equals is connected.
No, it is not.
Yeah, it is.
If
Pick-
X is not equal Y.
Pick any two X and Y's where they're not equal. Oh, no,
Then
you're right.
3 equals 4 and 4 equals
So it's
6.
not connected, but it is strongly connected. Right?
No.
No, it's neither.
Times up there playing games with himself. Almost got you, Tom.
You don't need to entertain yourself all day.
Okay. Next one, A cross A. Is that one strongly connected?
Yes.
Yes.
Yes. So once again, the only things that could be strongly connected were the ones that were connected, right?
Yes. But not every connected is strongly connected.
Okay. So that covers those properties. Now, if a relation happens to satisfy 3 of those properties, 3 special properties here, then we call it an equivalence relation. So an equivalence relation is a relation that is reflexive, symmetric, and transitive.
That means they equal each other?
No, then it's an equivalence relation. This isn't equality as in the identity symbol. Give you a common example of an equivalence relation. Congruent. Congruent is an equivalence relation.
Every point over here.
Every triangle is congruent to itself. If triangle X is congruent to triangle Y, then triangle Y is congruent to triangle X.
Yeah.
And then if X is congruent to Y and Y is congruent to Z, then X is congruent to Z. So, in all our different fields of maths, a lot of times when we're trying to say that these things are the same in some respect, then that relation that we're using to talk about how they're the same is going to be one of these equivalence relations. So congruence in geometry is a equivalence relation. One, when we go through topology that we're going to talk about a lot, is a homeomorphism is a congruence relation. You might have heard of an isomorphism before? No? No. Let's see another one. Another equivalence relation. Is the same height. Is the same height is an equivalence relation. Are you the same height as yourself? Yes. If you're the same height as me, am I the same height as you?
Yes.
Yes. If you're the same height as me and I'm the same height as Jill, are you the same height as Jill?
Yeah, sure.
Yeah. So it's reflexive, symmetric, and transitive. So let R be a relation on A. We say that R is an equivalence relation provided it is reflexive, symmetric, and transitive. Feel like you understand
It
what
has
I
to
need?
be all three
Yeah.
for it to be an
Yes,
equivalence
it has to satisfy. It has to have all three of those properties for it to be an
But
equivalence
it could
relation.
also satisfy some of the other ones.
So a trivial example is equals is an equivalence relation. Another example is A cross A is an equivalence relation. I think that those were the only ones up there. Another one is a sibling of. Is, well, I don't know, technically, are you your own sibling? If we allow you to be your own sibling, I don't know the exact definition, then is a sibling of, then is also an equivalence relation, right? So, when you have an equivalence relation, then you're able to take a set of things and start dividing it up. So an equivalence relation we might use is something like has the same last name, right? Now notice if we applied has the same last name to this class, you'd split us up into Timpsons, Barlows, and Hudsons. Couple more of one than the other. But, so an equivalence class, let's just say it and then we'll do more examples. So let R be a relation on A and let A be some element in A. So for our example, we'll say R has the same last name and we'll pretend A is Jacob. Then the equivalence class, which we signify like this, so Jacob's equivalence class is equal to the set of all people in this room such that they're related to Jacob.
In the relation.
Or has the same last name as Jacob.
Right.
Right? So, if we apply an equivalence relation to a set, we can split everyone up into an equivalence class. And everyone is going to belong to one and only one of those equivalence classes. Right?
Yeah.
So if we split us up by last names into different groups, you're each going to be in one and only one of those classes. And if Jacob has the same last name as James, then James has the same last name as Jacob. If Jacob's equivalence class and James's equivalence class are the same, then Jacob is related to James. And if they're not the same, then they're not related. This is an if and only if, right? That means this implies this and this implies this. Or another way we can say that is this implies this and not this implies not this. That's two equivalent ways to think about an if and only if statement. Okay? Another way that we talk about equivalence classes is we say that they partition up a set. We take all the elements in a set and we put them into one and only one partition. So if you think about, let's think of another example. So let's say at the start of a school day, we'll view A as the entire student body, and we'll say has discrete math first period, or what would be the relation? Is in the same class as, for your first class of the day, right? Then everyone in discrete math would be in one group, everyone in literature would be in another group, everyone in English would be in another group, right? Yeah, in the same class is not same grade or anything like that. You know what I meant by same class?
Yes.
Yeah, sorry, that's probably a weird one for you guys. Yeah. Let's see this. If R is an equivalence relation on A, then for every element in A, there exists one and only one equivalence class that A belongs to.
Right.
That's what I'm trying to say here. This is kind of messy, but I was running out of space, so I just wrote it in a weird notation. Does that make sense? Okay. So equivalence relations are a useful way for us to split up a set into different classes, different sets. Right? It's a way that we could organize a set into a bunch of subsets. We could use an equivalence relation to do that. We could take all the triangles in all of geometry and we could split them up into the ones that they're congruent to. And we could class them that way, right?
Yeah.
Okay. That finishes relations. And then so next time we'll continue, we'll start talking about functions. So we'll do functions, assuming we get through functions next time, then we'll start doing examples, and then